Hello children, once again welcome back to Physics with Sanoop. See, in this video we will be discussing all the previous questions from the chapter Current Electricity. Okay, so the first question is the resistance of platinum wire at 0 degrees Celsius is 2 ohm and 6.8 ohm at 80 degrees Celsius. Temperature coefficient of resistance of the wire is. See, this is the formula. Alpha, temperature coefficient of resistance, R with a suffix T, that is the resistance at T degrees Celsius, R0 resistance at 0 degrees Celsius, and T is the temperature. Okay, then it's given that resistance at 80 degrees 6.8, at 0 degree it is 2, okay, divided by 2 into 80. So in the numerator we will have 4.8 and the denominator it is 160. This 160 can be expressed as 1.6 into 100. 4.8 by 1.6 will be 3. When this 100 is taken to the numerator, it will become 10 raised minus 2. Okay, so 3 into 10 raised to minus 2 per degree Celsius means this must be the correct option. Okay. Now, a resistance of a carbon resistor determined from color codes is 22,000. Okay, 22,000. Okay, with the plus or minus 5% tolerance, the color of third band must be. See, in color code of carbon resistors, the first two bands represent the first two significant digits. Here, the first two significant digits are 2. Okay, the third band will represent the decimal multiplier, means the power of 10. Okay, now here the resistance will be 22 into 10 raised to 3. Okay, so the power of 10 is 3. Power of 10 is 3. Okay, so the third digit should be representing the digit 3. Okay, 3. Okay, what is the question? The color of the third band. It must be the color which represents 3. Okay, see B, Roy, that we have studied. Okay, this is black, this is brown, this is red, this is orange. So, for 3, corresponding to 3, the color should be orange. Okay, so this must be the correct option. Okay, now see a copper wire of length 10 meter and radius 1 by root pi centimeter has electrical resistance of 10 ohm. The current density in the wire for an electric field of strength 10 volt per meter. Current density means current through unit cross-sectional area. See, this is the formula for resistance, rho L by A. Rho is the resistivity, L is the length and A is the cross-sectional area. Now, see, we know that the Ohm's law is V equal to Ri. V equal to Ri. Okay, now see, this is R. Okay, then Ohm's law V equal to Ri. Okay, now see, let me take this L to the left. Okay, so it will become V by L. Then I by A, that is the current through unit area or it is the current density, and then rho. Okay, see, L is taken to the left, I by A, then rho. Rho is the resistivity. See, from here we will get resistivity. Okay, resistivity rho will be equal to CR A divided by L, that is resistivity. Okay, so V by L is the intensity of electric field capital E, capital I by A is the current density J, and RA by L, that is the resistivity. Okay, now we have this current density J equal to, take this L to the left, so it will be E into L in the numerator and denominator will be RA. A is the cross-sectional area and it can be expressed as pi r square. Okay, now the EMF is given as 10 volt per meter, length is given as 10 meter. Okay, and the denominator resistance is also 10 ohm. Okay, then pi r square, pi, radius is 1 by root pi centimeter. Centimeter can be converted as meter by multiplying with the 10 raised minus 2. So, 1 by root pi whole square will be 1 by pi and pi can be cancelled, means this and this can be cancelled. Okay, now 110. Okay, this 10 and this 10 can be cancelled. 10 raised to minus 2 whole square will be 10 raised minus 4. When it is taken to the numerator, it will become 10 raised to plus 4. Already there is a 10, so it will be 10 raised to 5 ampere per meter square. Ultimately, okay, 10 raised to 5 ampere per meter square. Next, a charged particle having drift velocity of 7.5 into 10 raised to minus 4 meter second raised minus 1 in an electric field of 3 into 10 raised to 11 volt meter raised minus 1 has a mobility in meter square volt raised minus 1 second raised minus 1, means mobility in SI units. See, mobility is actually the drift velocity per unit intensity of electric field, or it is drift velocity by intensity of electric field. So this is 7.5 into 10 raised minus 4 divided by 3 into 10 raised to 11. 7.5 by 3 is 2.5. When this 10 raised to 11 is taken to the numerator, it will be 10 raised to minus 11. Already there is 10 raised minus 4. So 10 raised minus 4 into 10 raised to minus 11 will be 10 raised minus 15. So 2.5 into 10 raised to minus 15 SI units. Okay. Now see a carbon resistor of 47 plus or minus 4.7 kilo ohm. Plus or minus 4.7 means it is actually 10% of 47. Okay, so the percentage tolerance is 10%. Okay, see, first two colored bands will represent the first two significant digits. Okay, first digit is 4 and the color band corresponding to 4 must be yellow. Okay, so the first one must be yellow. Okay, first one must be yellow. Okay, then next is 7. The colored band corresponding to 7 is violet. So next should be violet. And third is kilo ohm, means it is 10 raised to 3. Okay, so the third band must be corresponding to the power of 10. It being 10 raised, kilo ohm, it is 10 raised to 3, or the band should be corresponding to 3. Okay, means it is orange. Okay, the last band shows the percentage tolerance. It is 10% and it is 10% is silver. Okay, so the next one should be silver. Yellow, violet, orange, silver. Yellow, violet, orange, silver. This must be the correct option. Okay. Across a metallic conductor of non-uniform cross-section, a constant potential difference is applied. The quantity which remains constant along the conductor is current. Only the current. Okay, only the current. Okay, current will be constant. Now see, I is NaEV. Okay, as we move from left to right, okay, number density will not change, electronic charge will not change, but the cross-sectional area increases and drift velocity will decrease accordingly. Okay, but the current will remain constant. Now, if you consider the flow of liquid through a pipe of cross-section like this, then the rate of flow will be constant. Okay, rate of flow is actually the product of area and velocity. Okay, so the rate of inflow here will be equal to the rate of outflow here. Okay, so here the rate of flow is A1V1 and here it will be A2V2. Okay, here is A1V1 and here it will be A2V2. Okay, now see, that is the rate of flow, and that A1V1 equal to A2V2, we call it as equation of continuity. Okay, anyway, here the current is constant throughout. A wire of resistance 4 ohm is stretched to twice its length. Okay, the resistance of the stretched wire would be, see, this is resistance R equal to rho L by A. And resistance R equal to, see, in the previous question we have derived this one, resistance R equal to rho D by M L square. So resistance is proportional to square of the length. Length is doubled. So the resistance will become 4 times. So R dash will be 4R. Okay, original resistance was 4 ohm. Now the resistance will be 4 times, means 4 into 4, it must be 16 ohms. Okay, so this must be the correct option. Silicon and copper. Silicon being a semiconductor, when it is cooled, its resistance will increase. Copper being a metallic conductor, when it is cooled, its resistance will decrease. Cooled. Okay, for silicon increases and for copper decreases. What? Resistivity. This is true. Okay, the first option. Now let's see A wire has a resistance of 3.1 ohm at 30 degrees Celsius and a resistance of 4.5 ohm at 100 degrees Celsius. Temperature coefficient of resistance of the wire will be. See, we have R1 equal to R0 into 1 plus alpha T1 and R2 equal to R0 into 1 plus alpha T2. Okay, where R0 is the resistance at 0 degrees Celsius and R1 is the resistance at T1 degrees Celsius. Okay, R1 by R2 will be 1 plus alpha T1 plus 1 plus alpha T2. Okay, R1 into 1 plus alpha T2 equals R2 into 1 plus alpha T1. And alpha will be R2 minus R1. Okay, divided by R1 T2 minus R2 T1. If we put the values, we will get, see, in the numerator 4.5 minus 3.1, that is 1.4. Here it is 310 and this will be 135. Okay, this is actually 45 into 3. Okay, 45 into 3, that is 135. So we will get 1.4 divided by 175. Multiply both sides, both numerator and denominator by 4. So here you will get 700 and then the numerator you will get 1.4 into 4. Okay, now see, this can be written as 700 can be written as 0.7 into 10 raised to 3. 0.7 into 10 raised to 3, right? Now 1.4 by 0.7 will be 2. Into 4, 8. 10 raised to 3 when taken to the numerator, it will be 10 raised to minus 3. It's really beautiful. It is 0.008 per degree Celsius. Okay, this must be the correct option. Right? It's a really beautiful, very good question. The masses of 3 wires of copper are in the ratio 1 is to 3 is to 5. And their length are in the ratio of 5 is to 3 is to 1. The ratio of their electrical resistances will be, see, R resistance we have again the same formula, that is resistivity density L square by M. Okay, so the resistance is directly proportional to L square by M. Okay, length are in the ratio copper, see, length are in the ratio 5 is to 3 is to 1. So L square will be 5 square, 3 square, 1 square. Mass in the ratio 1 is to 3 is to 5. Mass 1, 3, 5. Okay, so here we have 5 square, then 3, 5 square, 3 and 1 by 5. Okay, children, multiply throughout by 5. Okay, here 25 into 5 will be 125. 3 into 5 will be 15. 1 by 5 into 5 will be 1. Okay, so 125 is to 15 is to 1. This must be the correct option. Okay, the equivalent resistance of the infinite network given below is, okay, now see, we want to find the effective resistance between these 2 points A and B. Okay, now see, this much is a section and this is an identical section. This is also an identical section. See, this is one section, then an identical section, then again an identical section. There will be such infinite sections. Okay, infinite sections. And suppose the effective resistance of such infinite sections connected like this. Effective resistance, let it be X. Let it be X. Okay. Now from this, see, infinite sections, suppose one section is removed, then how many sections will be remaining? Infinity minus 1. That is infinity itself. So if you find the resistance from these 2 points, the effective value is X. Okay, now remove this first section. Then A will come here and B will come here. Okay, and see, again there will be infinite sections and the effective resistance still will be X. Okay, now see, this much, see, this much can be replaced with a resistance X. Okay, so if you find the resistance from here, it will be X, and the resistance of this much section, that is also X. Okay, here is the network. Okay, now this part is replaced by X. Okay, See, if you find the resistance from here, there will be infinite sections. If one is removed, then also infinite sections. Okay, so if you find the resistance between these 2 points, it is x. Between these 2 points also x. Okay, here is the finite network in which this x and 1 are in parallel. Okay, that parallel combination in series with 1 and 1. Okay, this will be 1 into x by 1 plus x. Okay, this one, then 1 and 1 in series, that will be 2. Okay, the effective resistance of this combination is equal to x itself. Okay, now if you simplify this, you will get this one, x square minus 2x minus 2 equal to 0, and we have to evaluate x or the roots of this quadratic equation, and finally we will get 1 plus root 2. Okay, x equal to 1 plus root 2 ohms. So this must be the correct option, 1 plus root 2 ohms. Now three resistors having resistances R1, R2 and R3 are connected as shown. The ratio I3 by I1 of currents in terms of resistances used in the circuit. Now see, these two resistors are connected in parallel. So the voltage across these two resistors will be the same. Here the voltage will be I2 R2 and here it will be I3 R3. Those two voltages must be equal. I2 R2 equal to I3 R3. So R2 by R3 will be I3 by I2. Let's go for the componendo dividendo rule. Okay, now see, numerator is kept as it is. Okay, now this numerator and denominator are added and put in the denominator. So R2 divided by R2 plus R3 on the left side. See, whatever you do on the left side, same thing should be done on the right side also. Okay, see, R2 by R2 plus R3, that will be equal to I3 by I3 plus I2. Okay, now see, I1 is coming at this junction. Okay, where that I1 will be divided into I2 and I3. Okay, by Kirchhoff's current law. Okay, Kirchhoff's current law, or let us say the junction rule. See, the incoming current I1 must be equal to outgoing I2 plus I3. Okay, now this I3 plus I2, that will be equal to I1. So I3 by I1, that is the required ratio, that will be equal to R2 over R2 plus R3. Okay, so this must be the correct option. Okay, now see, otherwise see, the same thing can be, we can go for an alternate method. See, the total current is I1. Okay, at this junction I1 will be divided into I2 and I3 into two resistors R2 and R3. Okay, and the current will be divided in the inverse ratio. Okay, see, the total current I1 will be divided into R2 plus R3 part. R2 plus R3. Okay, now the current through R3 will be proportional to R2 and current through R2 will be proportional to R3. Okay, because the current will be divided in the inverse ratio of resistances. Okay, current through R2 and R3 will be in the ratio of R3 and R2, right? So I1 will be divided into R2 plus R3 equal part. Okay, current through R3 will be proportional to R2. So this is I3. Okay, so I3 by I1 will be R2 divided by R2 plus R3. Okay, same result we will get. A ring is made of a wire having resistance 12 ohm. Find the points A and B as shown in figure at which a current carrying conductor should be connected so that the resistance R of the sub-circuit between these points is equal to 8 by 3 ohm. Okay, see, the total resistance is 12 ohm. Okay, so R1 plus R2, suppose the resistance of this part is R1. Okay, it is of length L1 and the resistance of this part whose length is L2. It is R2. So R1 plus R2 must be 12. Okay, and the effective resistance R1 R2 by R1 plus R2 must be 8 by 3. It is given like that, 8 by 3. Okay, now this is R1 plus R2 is given as 12. When it is taken to the other side, we will get R1 into R2, that is 32. So R1 and R2 are such that their sum is 12 and their product is 32. So you have to find the factors of 32. Okay, factors of 32. See, factors of 32 are, see, 16 and 2. Okay, 16. Factors of 32 are 16 and 2. But their sum is not 12. Okay, then the factors are 8 and 4. And their sum is 8 plus 4, 12. So, R1 and R2 must be 8 and 4. Okay, 8 and 4. So, L1 by L2 must be 4 by 8 or it is equal to 1 by 2. Okay, L1 by L2 must be 1 by 2. When a wire of uniform cross section A, length L and resistance R is bent into a complete circle, resistance between any two diametrically opposite points will be. See, the total resistance is R. It is bent into a circle. Okay, so the resistance of this part will be R by 2. The resistance of this is also R by 2. These two are connected in parallel. So R by 2 and R by 2 in parallel, effective will be R by 4. Okay, this is R by 4. The current I in the given circuit is, okay, see, here we have 6 ohm and 6 ohm. This is 6 and 6 in series. So the effective resistance will be 12 and the voltage across this 12 is 4.8. So the current through this branch I2, okay, current through this branch I2 will be 4.8 by 12, that is 0.4. Now here the resistance is 3 ohm. The voltage across this 3 ohm is also 4.8. Okay, so the current through 3 ohm, that is I1, that is 4.8 divided by 3, that is 1.6. Okay, so here is 1.6 and the current through here, this one is 0.4. So the total current drawn from the cell will be 1.6 plus 0.4, that is equal to 2 ampere. Okay, so it must be 2 ampere. Now the current in the following circuit is, see, here we have a 3 ohm, the voltage across is 2 volt. So the current through that 3 ohm will be 2 by 3. Okay, so I1 is 2 by 3. Here we have 3 and 3 in series, effective will be 6. The voltage across it is also 2 volt, so the current through it will be 2 by 6, that is 1 by 3. Okay, current through this one is 2 by 3 and current through this branch is 1 by 3. So the total current will be 2 by 3 plus 1 by 3, that is equal to 1 ampere. That much will be drawn from the cell. Okay. Now let's see what we have next. What will be the equivalent resistance of the circuit shown in figure between points A and D. A and D. Okay, means between this point and this point. Okay, now see, this resistance won't come in the circuit. Okay, similarly this one also. Now this 10 and this 10, these two are in series. It is equivalent to 20 ohm. These two are also in series, it is also 20 ohm. Now these 20 and 20 are in parallel, it is equivalent to 10 ohm. Okay, so here the total is 10 ohm. Okay, now here we have a 10, okay, in series with another 10 and one more 10. So total will be 30 ohm. Okay, 10, then again 10, then 10, 30 ohm. So this will be the effective resistance. Now let's see what we have. Two wires of same metal have length but their cross sections are in the ratio 3:1. They are joined in series. The resistance of thicker wire is 10 ohm. The total resistance of the combination will be. Now see, they have the same length but their cross sectional areas are different. Okay, so R is proportional to 1 by A. So R1 by R2 equal to A2 by A1. Okay, suppose the first one is thicker, it's a resistance. A thicker wire has a cross-sectional area 3 times. So A2 by A1 will be 1 by 3. And it is given that R1 equal to 10 ohm. So R2 will be 3 R1, that is equal to 30 ohm. Okay, so the effective resistance will be 40 ohm. This one, R1 plus R2. Okay, now let's see what we have next. In the circuit shown in figure, the current in 4 ohm resistance is 1.2 ampere. Okay, here current through this one is 4 ohm is 1.2 ampere, so the voltage will be 1.2 into 4, that is 4.8. Okay, see, the voltage across this is 4.8. Now this one is parallel to this 4 ohm. So the voltage across these two resistances will be the same. Okay. So the voltage across this 8 ohm, that is 4.8. So the current through it will be 4.8 by 0.6 by 8. Okay. 4.8 by 8. That will be 0.6. Okay. Now see, 0.6 is coming, 1.2 is also coming. So the current, this will be 1.8. 1.8. Okay. And the voltage across this 2 ohm resistance, that will be 1.8 into 2, that is equal to 3.6 volt. Okay. What is the potential difference between B and C? That is the potential difference across 2 ohm. That is equal to 3.6 volt. So this must be the correct option. Now let's see, you are given several identical resistances, each of value 10 ohm and each capable of carrying a maximum current of 1 ampere. It is required to make a suitable combination of these resistances of 5 ohm which can carry a current of 4 ampere. See, each resistance can carry a maximum of 1 ampere, but we have to carry 4 ampere. So there should be 4 branches. Okay, there should be 4 branches, 1, 2, 3, 4. Because in each branch the maximum current that can be passed is 1 ampere and we have to pass 4 ampere. So there should be 4 branches. Effective resistance should be 5 ohm. Okay. See, if all the 4 branches are identical and if the resistance of each branch is say X, then this is X, this is X and this is X, this is X. Effective resistance will be X by 4 and it is equal to 5. Effective resistance should be 5. X by 4 is 5. So X should be 4 into 5, 20. Means the resistance of each branch should be 20. Okay, we have resistances of 10 ohm each. And in each branch we require 20 ohm. So these 10 ohm resistances, 2 of such resistances should be connected in series. Okay, here 2 are connected in series. Effective will be 20. Here also 20, here also 20, here also 20. 20, 20, 20, 20. 4 identical resistors are connected in parallel. Effective will be 20 by 4. So it will be 5 ohm. That's fine. We need an effective resistance of 5 ohm. Okay, the current through each resistance is only 1 ampere. And the total current carried by the circuit is 4 ampere. Everything is fine. Okay, the minimum number of resistances required. In each branch we require 2 and such 4 branches. Total number of resistances required will be 8. Okay. Now let's see in the network shown in figure, the resistance is 1 ohm. The effective resistance between A and B is. Okay, now in order to find the effective resistance, if we connect a cell like this, current will be drawn out of the positive pole. Whatever current is drawn from the positive pole should be supplied back to the negative pole. Okay, so now see, this is line of symmetry. Okay, whatever resistances are connected to the positive pole, similar resistances are connected to the negative pole also. So from the positive pole, whatever current is drawn by this branch, say I1, that will be supplied to the negative pole through this I1. Okay. Now if the current through this one is I2, okay, same current must be passed through this one I2. Okay. Now whatever current is drawn through this, it must be fed back through this. Okay. Whatever current is drawn from the positive pole through this half of this resistor, the same thing will be fed back to the negative pole through the other half. Okay. See, the resistances connected to the positive and negative are exactly identical. Okay. Now see, the current I1 coming like this going straight. Okay. And current I2 coming like this going like this. So this is not a real junction where there is no mixing of currents. Okay. So that point can be detached, because in here also I1 will be going like this and I2 will be going like this, no difference at all. Okay, so here we have R and R, this R and R in series, that is 2R. That is in parallel with another R, so this will be 2R in parallel with R, that is 2R by 3. Okay, now here we have R. Okay, R, then 2R by 3, then again R. Children, this R can be expressed as 3R by 3. See, this is R means 3R by 3. 3R by 3, 2R by 3, again 3R by 3. Find the sum. 3R by 3 plus 2R by 3, that is 5R by 3, plus again 3R by 3, that is 8R by 3. So whole thing, this will be 8R by 3. 8R by 3. That is in parallel with 2R. 8R by 3 in parallel with 2R. Okay. 8R by 3 in parallel with 2R. Means what? 8R by 3 in parallel with 2R. 8 by 3 in parallel with 2. Okay. 8 by 3 in parallel with 2. See, this 2 can be expressed as 8 by 4. So 8 by 3 in parallel with 8 by 4. What you see, this 8 by 3 can be considered as 8, 8, 8, 3 identical resistors connected in parallel. And this 8 by 4 can be considered as 8, 8, 8, 8, 4 identical resistors connected in parallel. So altogether here 3 and another 4. 7 identical resistors each equal to 8 are connected in parallel. So it is simply 8 by 7. Okay, 8 by 7 ohm. Right? Now next two batteries of EMF 4 volt and 8 volt with internal resistance 1 ohm and 2 ohm are connected in a circuit with a resistance of 9 ohm as shown in figure. The current and potential difference between the points P and Q. Children, see, in an electrical circuit, you can slide a point, but you can't jump over an element. Means you cannot jump over a resistor or a capacitor or an inductor or a resistor. You know, see, you can slide a point, but you can't jump over a component. Means this point is P. This point P can be slided like this. Okay, this also will be capital P. Means electrically these 2 points are identical. Okay, now see, there is zero resistance between these 2 points P and these 2 points, zero resistance. So if there is a current, even though there is a current through this wire, the voltage or potential difference between these 2 points will be current into resistance. That resistance is zero, means the voltage between these 2 points is zero. Potential difference is zero, means the potential here and here are the same, or these 2 points are electrically identical. So if this is capital P, this is also capital P. Okay, now if this is capital Q, this also will be capital Q. See, actually you have to find the potential difference between these 2 points. See, there is there are a large number of elements between these 2 points, but these 2 points P and Q are identical to these 2 points P and Q, and there is only one element between these 2 points P and Q. So instead of finding the potential difference between these 2 points, you can find the potential difference between these 2 points. That will be relatively easier. Okay, now let's see. Current will be always out of the positive pole. So this 4 volt cell will send a or try to send a current like this. Okay, and 8 volt in the opposite direction. So this 4 volt and 8 volt will be opposing each other. Okay. So the resultant current will be along the direction in which the 8 volt will try to send a current. Right? Okay, so the resultant current will be like this. Okay, that is the direction in which this cell of higher EMF sends a current. Okay. Now the resultant EMF will be 8 minus 4 and total resistance will be, here we have 1, okay, here we have 2 and here we have 9. So 1 plus 2, that is 3 plus 9, 12. Okay, so current will be 8 minus 4 divided by 12, or that is 1 by 3 ampere. Okay, and here we have resistance capital R, that is equal to 9. So the voltage between these 2 points will be 9 into 1 by 3, or it will be 3 volt. Okay, now see, the current is 1 by 3 ampere and the voltage is 3 volt. So this must be the correct option. Okay, next the total power dissipated in watts in the circuit shown here is okay. And let's see, here we have this 6 ohm. These currents are not given. Okay, only the diagram is given. Here we have 3 ohm and 6 ohm in parallel. So the effective resistance will be 3 and 6 when they are connected in parallel. Effective will be 2 ohm. Now that 2 ohm and 4 ohm are in series, total resistance will be 4 plus 2, 6 ohm. Okay, the voltage is 18 volt. So the current drawn from the cell will be 18 divided by 6, that is equal to 3 ampere. Okay, 18 by 6, that is equal to 3 ampere. Okay, so the total power will be, okay, so 3 ampere will be coming like this. Okay, so the current through this will be 2 ampere and the current through this will be 1 ampere. How do we know that? See, the resistors are in the ratio 3:6 or 1:2. So current must be in the reverse order, 2:1. So the total current drawn is 3 ampere. That is to be divided in the ratio 2:1, means 2 plus 1, 3 equal part. Each part will be 1 ampere. Okay, current through smaller resistor must be 2 parts. So 2 into 1, that is 2 ampere, and here 1 ampere. Then only the voltage across these two will be equal. Okay, so the power dissipation here will be 3 square into 4. Okay, and that is shown here, 3 square into 4. Okay, power dissipation here will be 2 square into 3. That is shown here, 2 square into 3. Power dissipation here will be 1 square into 6. 1 square into 6. So 6 plus 12, 18, plus this is 36. So it will be 54 watts. 54 watts. Okay, or we can do the power dissipation as V square by R. What is the effective resistance? That is 6. And the effective voltage is 18. So 18 square by 6. So 18 into 18 divided by 6. Okay, now this 6 and 18 can be cancelled. We will get 3 here. Okay, V square by R. Okay, so 18 into 3, that also will be 54 watts. Now let's see, power dissipated across the 8 ohm resistor in the circuit shown here is 2 watts. Okay, here it is 2 watts. Okay, and the power dissipated in watt units across 3 ohm resistor is, okay, see, suppose the current through 8 ohm is I2, then the power dissipation will be I2 square into 8. I2 square into 8, that is given as 2. Okay, so I2 square will be 2 by 8, or that is 1 by 4. So I2 will be root of 1 by 4, or it is 0.1 by 2, or it is actually 0.5. 0.5 ampere. Okay, that is the current through this 8 ohm resistor. So the voltage across it will be 8 into 0.5, that is 4 volt. The same 4 volt will be there across this combination also. Okay, so across this combination the voltage is 4 volt and the resistance is 3 plus 3 and 1 in series, so 3 plus 1, 4. So the current through this one, I1 will be 4 volt by 4 ohm, that is 1 ampere. So 1 ampere current must be passing through this series combination. We have to find the power dissipation in 3 ohm, that is I1 square into 3. Okay, I1 being 1 ampere, I1 square into 3 will be 3 watts. Okay, 3 watts. So this must be the correct option. Next, two 220 volt 100 watt bulbs are connected first in series and then in parallel. Okay, when they are connected in series, effective power will be half. When they are connected in parallel, effective will be twice. Okay, so first is half, means 50 watts, and then 200 watts. Okay, 50 watts and 200 watts. This one. Now for the network shown in figure, the value of the current is, okay. Now here we have a Wheatstone's bridge and we have to check whether it is balanced or not. Okay, these two are the opposite arms. For a bridge to be balanced, the product of the opposite arms should be equal. See, this is 4 into 3, that is 12. Then 6 into 2, again 12. So bridge is balanced. There won't be any current through this branch, so it can be eliminated. Then you will get this 4 and 2 in series, that is 6. Now this 6 and 9 are connected in parallel. Now that 6 can be considered as parallel combination of 3 identical resistors, each equal to 18 ohm. Means 6 can be expressed as 18 by 3. Means 18, 18, 18 connected in parallel. That will give you 6. And here you have 9, that can be considered as 2 identical resistors, each equal to 18 ohm connected in parallel. 18 and 18 in parallel. Okay, so this parallel combination is in parallel with another combination. Okay, all resistors are identical, each equal to 18. And how many such resistors are connected in parallel? 3 plus 2, that is 5. So it will be 18 by 5, or we can say, okay, that is the effective resistance, and current will be V divided by 18 by 5 or 5V by 18. Okay, this is the effective resistance, okay, and this will be the answer, 5V by 18. Next, 5 equal resistances, each of resistance capital R are connected as shown in figure. A battery of V volt is connected between A and B. The current in the AFCB, okay, AFCB, okay, AFCB, right? AFCB means we have to find the current through this branch, okay, current through this branch. Now see, keeping this point E fixed, okay, now take this point like this, okay, here this will be B, okay. And now this A can be taken like this, okay. So ultimately you will get the network like this, okay. All the resistances are equal, so bridge is balanced. There won't be any current through this one, it can be eliminated. Okay, so this R and R in series, that is connected across V. This R and R again in series connected across the same voltage V. So current through this will be V by 2R. Current through this also will be V by 2R. Okay, we have to get the current through AFCEB, right? Okay, that is equal to V by 2R. A meter bridge. The balancing length from left end when a standard resistance of 1 ohm is in the right gap is found to be 20. The value of unknown resistance is X by R equal to L by 100 minus L. L is given as 20. Okay, so X by 1 equal to 20 divided by 80, that is 1 by 4. So X will be equal to 1 by 4 or 0.25 ohm. Okay, so this must be the correct option, right? Okay children, now everything is over. See, we have discussed all previous questions from this chapter, and see, as this potentiometer is deleted from the syllabus, I haven't discussed the questions from that topic. Okay, thank you.